Okay, so have you ever thought about like what makes that perfect swing push? You know, the kind that sends you flying higher and higher.
Like a playground swing.
Yeah,
Huh.
exactly. Like when you're a kid and someone pushes you at just the right moment and you just keep going up and up.
Right, right.
Well, that, my friends, is resonance in action.
And the amazing thing is that same principle, it's like it's happening all around us constantly.
Seriously, and at all these different levels, right? Like we're talking about from the air we breathe to like the tiniest atoms. It's wild.
It really is incredible when you start to think about it.
Okay, but before we get ahead of ourselves, let's break down what resonance actually means. I will say, I was looking at some of this Feynman stuff you sent over, and wow, I'm already feeling a little,
A little intimidated.
maybe just a touch, but also like really excited to dig into this.
Well, you're right to start with the basics. Just like that swing, everything has kind of a natural rhythm to it,
Okay.
a frequency it vibrates at. And when a force hits that system at or near like its sweet spot frequency, boom, resonance happens. It's like the system suddenly just like finds its groove.
So it's like the more in sync things are, the stronger the response.
Exactly. It's like the system is suddenly able to absorb way more energy, and that leads to a much bigger response.
So like picture a singer hitting that perfect high note and suddenly, bam, a glass shatters across the room.
Exactly. That's a classic example of resonance. It's like the sound waves from the singer's voice are syncing up perfectly with the natural frequency of the glass, causing it to vibrate uncontrollably until...
So it just can't handle it anymore.
Exactly. It's pretty amazing when you think about it. And speaking of things vibrating, did you know that even the Earth's atmosphere has a resonant frequency?
Wait, the entire atmosphere is like resonating. What's like pushing it? Is it the moon? I feel like I remember something about that from the material you sent over.
You're exactly right. The moon's gravitational pull, it's like a gentle nudge on the atmosphere, kind of like that swing we were talking about. And this pull creates these, well, they're subtle, but they're incredibly vast oscillations in the air around us.
Okay, that's like next level mind blowing.
Yeah.
But I have to ask, why should we care about the atmosphere humming along to the moon's tune? Like, what's the practical side of all this?
Well, for starters, it turns out that understanding how the atmosphere resonates is actually super important for things like, predicting long-term climate patterns and stuff. And remember that whole Krakatoa eruption?
Yeah, that was a massive volcanic explosion back in the 1800s, right?
Exactly. It was so powerful that it sent shockwaves through the atmosphere,
Wow.
creating these global oscillations. And get this, by studying those oscillations, scientists were able to accurately confirm the Earth's atmospheric resonance frequency.
Wow, talk about I mean, I don't want to say silver lining to a catastrophic event, but
Right, right.
that's incredible. But this whole resonance thing, it's not just about planets and atmospheres, right? I mean, I was looking at this research about like salt crystals.
You're catching on. Resonance happens at all scales, even in the tiniest of objects. A salt crystal is a great example. Those crystals, they're made up of a very specific repeating pattern of atoms.
Okay.
And you guessed it, that pattern has its own resonant frequency.
So you're telling me that even something as small and like seemingly simple as a salt crystal has its own unique vibration.
It does. And what's even cooler is that this resonance, it's related to how the crystal interacts with light,
Right.
specifically infrared light. Think of it like this.
Hmm.
The crystal only wants to absorb light that's vibrating at its specific frequency, like, I don't know, like a picky eater only wanting certain foods.
So is that how like heat vision goggles work? By tapping into this whole infrared resonance thing?
You got it. Those goggles, they pick up on the infrared light that's emitted by objects, which is directly related to their temperature.
Oh,
It's a great example of how understanding resonance at like a fundamental level can lead to practical technologies.
so it's like this hidden language of the universe, these vibrations and frequencies kind of dictating how things interact and behave. We've gone from pushing a swing to the Earth's atmosphere vibing with the moon's pull to tiny salt crystals resonating with infrared light. I mean, it's pretty amazing how this one principle, this resonance thing, plays out across such vastly different scales.
It really highlights the interconnectedness of everything in the universe, wouldn't you say? But we're just getting started. We haven't even touched on how resonance plays out in the world of atoms and even smaller particles. Remember that research you shared about a physicist named Dr. Mussbauer?
Oh, right. He's the one who won a Nobel Prize for his work with resonance, right?
Mm.
Didn't it say his experiments had to be incredibly precise?
They did. Dr. Mussbauer was working at, like, the cutting edge of atomic physics. And his experiments involved measuring these incredibly tiny changes in energy levels within the nuclei of atoms. Like, imagine trying to measure something a million times smaller than the width of a human hair. That's the level of precision we're talking about.
Okay, I think I'm getting flashbacks to high school physics just trying to imagine that. But what makes his work so significant? What did this, like, ultra-precise resonance actually reveal?
Well, you see, before Nussbauer's discovery, physicists thought that achieving such sharp resonance in something as, well, as complex as an atom's nucleus was practically impossible. It was like trying to hear a single whisper in the middle of a hurricane.
Wow.
But Nussbauer, he found a way, and his discovery, well, let's just say it revolutionized several fields.
Okay, I'm definitely all ears. What kind of revolutions are we talking about here?
Well, for starters, his work had this huge impact on things like archaeology and geology. Like, for example, it allowed scientists to date ancient artifacts and rocks with incredible accuracy. Yeah, by analyzing the resonant frequencies of their atoms.
Oh, wow. So this is how we can tell if something is, like, really 1,000 years old or just a clever fake. Resonance detectors at the museum. Here we come.
Aha, exactly. And it gets even better. Nussbauer's work, it also helped us understand the Earth's magnetic field in much greater detail.
Okay, how so?
Well, you see, by studying how the resonant frequencies of atoms and rocks vary depending on, like, their location and age, scientists could actually piece together a history of the Earth's magnetic field over millions of years.
Okay, that's seriously impressive.
Mm.
Who knew that such, like, tiny, precise measurements could unlock secrets about the Earth's history on such a grand scale?
It's a testament to the power of fundamental research, for sure. But this deep dive into resonance, it doesn't stop there. We're about to enter a realm where things get even weirder.
Okay, now you've really piqued my curiosity. We're going beyond atoms now. What could be stranger than that?
Well, remember that article we talked about earlier, the one from Physical Review about the K-meson?
Right? Wasn't that the one about particles being fuzzy or something like that?
That's a great way to put it. You see, when physicists started smashing atoms together at really, really high speeds, they discovered all sorts of new particles they'd never seen before. One of these was the K-meson.
Okay, so what's so special about this K-meson?
Well, the K-meson is a great example of how resonance can kind of blur the line between what we think of as a particle and a wave. Imagine, like a wave in a swimming pool, right? But this wave, it's so well defined and stable that it almost behaves like a separate object, like, say, a beach ball bobbing along.
I'm trying to picture it.
That's kind of what's happening with the K-meson. It's like a resonance that's taken on a life of its own in a way.
So is it a particle or is it a wave? I feel like my head's starting to spin a bit here.
Haha, yeah, that's the million-dollar question in particle physics.
Nah.
The discovery of resonances like the K-meson, it challenged our traditional understanding of these fundamental building blocks of matter. It suggests that the universe might be even more complex and interconnected than we ever imagined.
Okay, this is honestly blowing my mind a little. We've gone from pushing a swing to the Earth's atmosphere humming along with the moon to tiny magnets in our bodies singing back to MRI machines, and now to particles that are also waves. I mean, where do we even go from here? So after, like, this whole deep dive into the world of resonance, I got to ask, what does it all mean? Are we saying that everything is just this big, blurry symphony of frequencies and vibrations?
Well, those are some seriously big questions, and to be honest, they're the kind of questions that physicists are honestly still wrestling with today.
Yeah, it's like one of those things where the more you learn,
The more you realize you don't know.
totally, but it's also kind of cool, you know?
Absolutely.
Like, it keeps things interesting.
It definitely does. But what we can say for sure is that discoveries like those involving the K-meson, they've, like, thrown this fascinating curveball into our understanding of the universe. It's like, we thought we knew the rules of the game, and suddenly the universe was like, nope, here's a whole new set of possibilities.
Uh-huh. It's like the universe is showing off.
Right.
So where does, like, resonance research go from here? What are those big unanswered questions that scientists are still trying to crack?
Well, one of the biggest mysteries is, like, whether there's a fundamental limit to how small things can get. We've gone from atoms to nuclei to particles like the K-meson, but could there be even smaller, even more fundamental units of matter out there?
It's like those Russian nesting dolls, but with, like, a whole lot more physics involved.
Exactly. And the more we learn about resonance, the closer we might actually get to understanding those fundamental building blocks of the universe.
It makes you wonder, like, what else is out there just waiting to be discovered?
And what role might resonance play in those discoveries?
It's pretty amazing to think about. Well, I think it's safe to say this deep dive has left me with maybe more questions than answers,
Mm.
but in the best way possible, of course.
That's the sign of a truly enriching exploration, isn't it? It's not always about finding all the answers, you know? It's about asking the right questions and appreciating just how incredibly complex and elegant the natural world really is.
Absolutely. So the next time you're listening to music, swinging on a swing set, or even just like heating up your dinner in the microwave, remember resonance. It's literally everywhere, shaping the world around us in ways we're only just beginning to understand.
And who knows what amazing discoveries await us as we continue to explore this fascinating phenomenon. One thing is for sure, though, the universe is full of surprises, and that's what makes it so captivating.